Hello, everyone. Welcome to this session. This is third of the three sessions featuring invited presentations from author of selected paper from the Computer Graphics and Application for magazine. IEEE CG&A features a mixture recruited magazine-style education and opinion pieces, as well as a core set of peer-reviewed research articles. The presentations in this session are all the peer-reviewed articles. The title of this session is Visualization, Teaching, and Literacy Continued, and Machine Learning for Viz, which is a bit complicated. The reason why is that we still have one paper from the Visualization, Teaching, and Literacy left from the author Charles Perrin that from the previous session, and the remaining of the five papers are selected from another special issue named powering visualization with deep learning. So this is our first presentation with what students learn with personal data physicalization by the author Charles Perrin. It will be recorded presentation, but let's thanks for the presenter and welcome for his presentation first. Yeah.
What do students learn with personal data physicalization? This is the question I asked myself while I was redesigning the visualization course I teach at the University of Victoria. It's a course for fourth year and graduate computer science and software engineering students. I wanted to explore the intersection of two topics: personal data visualization that has the potential to increase student motivation and creativity, and constructive visualization with physical material that we know has many benefits for novice visualization learners. At the intersection, I was hoping to spark creativity among students who too often underestimate their creative capabilities and are cursed by their technical knowledge. In this 6-part assignment, students created physicalizations of data they collected. First, they collected 1 week of data and formulated 3 questions they would like to find answers to, with an emphasis on time. Then they designed physicalizations with a temporal component and provided rationale for their choice of materials, visual marks, and visual variables. They collected 1 more week of the same data and formulated 3 new questions. Then they designed physicalizations that addressed comparison questions about their 2 weeks of data. Then they combined their 2 designs to address as many of their questions as possible. And last, they submitted a 3-minute video that described their data, their designs, some personal data insights, and a reflection on the process. This assignment was designed so that students achieve 4 of the course intended learning outcomes. Students developed an understanding of data collection through the data collection and reflection stages. They formulated questions that visualization can help address and created design variations through the data collection, formulation of questions, and ideation stages. And they combined different visual marks and visual variables in the ideation stages. Overall, students did great in this assignment. They enjoyed the process and they achieved the learning outcomes. But based on their feedback that the deliverables were redundant, I simplified the assignment, keeping the same learning outcomes, but including only 1 data collection phase, 2 weeks of data, and 1 design ideation phase. With ethics approval, I could collect and analyze the material created by students in the course. Participation from students was not mandatory, and I was blind to their participation. The data I analyzed consists of written assignment deliverables, the video report, and the written report in which students reflect on their learning for the entire course. Note that images and videos are de-anonymized on the request of participants. The findings from this analysis are grouped under 7 categories: data collection, physical and visual mappings, interactions, sharing and storytelling, personal insights, a different perspective, and finding creativity. In terms of data collection, 1/3 of the students found data collection painful, saying it was very time-consuming and that tracking the data consistently is hard. This made them elaborate data collection strategies. For example, at a point, one student started taking photos inside their pocket using a phone shortcut. They didn't care about the photo itself, but this was a way to collect time, date, and location stored in the metadata of a photo. 2/3 of the students combined automatic and manual data collection methods. They used apps and websites like MyFitnessPal, ScreenTime, Last.fm, Fitbit, and Google Timeline to retrieve data. But they complemented with manual logging, often on their phones, sometimes using pen and paper. And the more the data was personal, the more students relied on manual data collection. Half of the students collected data related to their mood, stress, or mental and physical health, data that is subjective and hard to collect automatically. In terms of physical and visual mappings, around half the students reproduced a standard chart, such as pie chart, line chart, bar chart, under many forms, and spider charts. The other half, though, created bespoke layouts and mappings like these ones, making great use of 3D, of material, of space, of transparency, perspective, and orientation, for example. They used unique properties of the physical world, such as liquid viscosity here, and others like shadows, perspective, and lighting. Or here P12 relied on gravity to push liquids down a pipe and reach an equilibrium. Students often use material that related to their data. Here rocks, ropes, and chalk are used to represent rock climbing activities, compact discs for music-related data, food for calorie, carbs, and fluid intakes, and pencils and forks for study time and meals. A handful of students also learned that an initial layout might not work forever as new data is being collected. For example, one student used plastic cups and fluids to represent their fluid intake. They realized as they were collecting more data that the scale they had chosen was not sustainable because it was taking too much space in their home. When it comes to interactions, several students commented that constructing the visualization made them more aware of their data, saying, for example, the act of physically laying out my diet on a table made me more aware of what I was putting into my body. One student out of 10 explored creative physical interactions. One common interaction makes use of rearrangeable layers that make comparison possible through transparency, or using viewing angle with a 3D layout. And here stringed star plots that each represent one data dimension can be overlaid for comparison. Others created rearrangeable structures. For example, here, each block represents one day with various data dimensions, and yarn connects consecutive days. But one can grab a few blocks to compare them more closely by bringing them side by side without losing the overall grid structure. Another student represented data values on a radial layout, with the distance from the center being the time of day for that day, and then by spinning the wheel, one could see what time of the day this data dimension is often present, although the student found that it didn't work that well. Next is sharing and storytelling. Several students mentioned sharing their physicalizations with friends and family and paid great attention to aesthetics and style. Over half of the students mentioned aesthetics and creativity when reflecting on this assignment, and they often designed cognizant that they would share their physicalizations and use them to tell stories to their close ones. For example, P62 said, "It's really fun to talk to people about how needy my cat is." Most students said they learned something about themselves through this assignment. They learned simple things, for example, about their eating habits, their mood, or their screen time. Or more surprising things. For example, students wrote that they were really surprised, that they found things odd, or that they became more cognizant. With the longer version of the assignment, a handful of students did act on their findings and change their behavior. One of them talked about how this project helped them improve their overall health, and another learned about how the activities they do influence their body while they were recovering from a knee injury at the time. This assignment also gives students a different perspective on visualization. Some realize that working under limited resources raises the challenges of limited space, of cost and availability of materials, and of time it takes to manually map data to physical variables. Other students saw these constraints as design opportunities. They found that it forced them to think more, to be more conscious of the process, and sometimes to get inspired by these limitations. I want to finish by reminding that at the beginning of the course, many students assume they are not creative and are afraid of even sketching. Although some students still end up creating relatively standard charts, many of them commented on how this assignment sparked their creativity. They found different sources of inspiration, were forced to being more creative and to set free their imagination. The use of physical materials allowed them to quickly see changes and ideate and help them understand the underlying mechanisms of visualization creation. Overall, students found that this assignment pushed them outside of their comfort zone in their software engineering or computer science degree. Personal data physicalization asks students to think about data collection, to explore new mappings, and to think about layout constraints, cost, and quantity of visual marks. It allows them to invent creative interaction techniques and to create objects they might share with their relatives. Not only does this assignment allow students to achieve visualization learning outcomes, it also allows them to learn things about themselves, to reflect, and to change, as well as to connect with their data in unique ways. I thank the students at the University of Victoria I interacted with in these courses, as well as the LTSI that funded the redesign of this course. You can find details about the assignment by following this QR code, and here are the pointers to learn more about the VIXI lab at UVic. Thanks for watching.
Just a quick reminder that you are welcome to use Slido to post your questions, Oklahoma Station 6. So we have a question from the audience. So the students share work in progress result. Did seeing others' physicalization inspire students to up their game?
Yeah, thanks. That's a very good question. Actually, the first time I did this assignment in the first version, they were a bit struggling because I didn't have good examples. So once I had taught it several times, I could start to have a database of examples to show. And now I have this publication and these videos that I can even show them to show like a wide variety of examples that of what other students create. And I think it changes a lot what they come up with. The first two times I would say I applied this assignment, I ended up with less interesting results, let's say, than afterwards. Once I could, so now every year I teach it. Like throughout the semester at the beginning, in the first few weeks, once in a while I will show some examples from previous years so that they can start about the data they collect, the materials they will use, etc., and get inspired. And I think the quality is improving a lot now that I am showing these previous good examples, but also some less good ones.
Here's the second question. What did you learn about yourself as a teacher for this course? Yeah.
I think the one thing that I did, at least, I don't know if I learned, but I did appreciate a lot, and I keep appreciating it, is that it's possible to enrich your teaching with research. And so one of the research directions that I like is around physical visualization. And so I know personal data visualization, so being able to design something at the intersection of these two topics of interest of mine, and seeing that it does result in very different things in terms of deliverables that students produce is very satisfying, because they also do, these kind of more regular projects, that I think most InfoVis course end up having, and it's not as exciting. The kind of insights they get, the kind of reflection they get on the process are very different. So I think I learned that it's worth trying to do some, teaching, research imbued teaching is really worth it.
Thank you. Thank you for the great talk and the answers. Let's thank the speaker again. So now we're going to have our second paper in the first paper in machine learning, and second paper in this session is DeepGD, a deep learning framework for graph drawing using GNN, presented by Xiaoqing Wang.
Hi everyone, my name is Xiaoqi Wang from The Ohio State University. Today I'm going to present a paper called DeepGD. The ultimate goal of this work is to propose a novel graph neural network-based deep learning framework for graph drawing, which can optimize any differentiable aesthetic criteria. Also, the generated graph layout can comply with multiple aesthetic criteria simultaneously. In graph drawing, most of the existing work only focuses on optimizing a graph layout toward a single aesthetic aspect. For instance, Nito focuses on minimizing the stress. TISNet tries to minimize the t-SNE score, which measures the distance between graph distribution and the layout distribution. Big Angle attempts to maximize the angular resolution, which is the angle formed by incident edges around the same node. In the literature, there is no consensus on which aesthetic aspect is the most important one. However, some researchers have shown that a good graph layout usually complies with multiple aesthetic criteria simultaneously. Therefore, in this work, we are trying to optimize multiple aesthetic goals simultaneously with a deep learning approach. Here is our model architecture. Basically, the input to our model is the adjacency matrix A, input layout X tilde, and edge feature matrix C. The output will be a matrix with the layout node positions. Our model is composed of a sequence of convolutional graph neural network layers. The basic idea of this convolutional GNN layer is that it updates the latent node embedding given the aggregated message from the neighboring node. For instance, for the first hidden layer, this red node embedding is computed from the aggregated message from its immediate neighbors. Therefore, this purple node embedding actually contains the information from nodes that are 2 hops away because it aggregates from the red node embedding of its neighbors. In this work, we stack multiple convolutional GNN layers together such that we can it allows us to gather both the local and the global information to generate visually pleasing graph layouts. Also, during our message aggregation process, the importance of the message depends on the information processing from the edge feature between node U and V. Given that this phi is a neural network trained for extracting useful information from the edge features. Please refer to our paper for more details about the model architectures. Here is our training process. For each graph, it will be fast-forwarded through a stack of convolutional graph neural network layers. Then we can get the generated graph layouts. Given multiple pre-specified aesthetic goals, we will evaluate the generated layout according to them. During training, we will practice drawing this graph over and over again to optimize toward the pre-specified aesthetic goals. The model actually learns to draw graph by minimizing the loss function. Since we try to optimize multiple aesthetics simultaneously, our loss function is composed of multiple loss components along with a weight vector alpha. This weight factor should imply how important we think the corresponding aesthetic is. However, there are 2 challenges we encounter in optimizing this multi-objective loss function. First of all, different aesthetics have different numerical scale, so the gradient of the multi-objective loss function is biased toward the aesthetic with the larger scale. We solve this issue by proposing a training strategy called adaptive weighting. Secondly, different objectives have different optimization characteristics. Therefore, it is difficult to ensure smooth and even optimization of multiple aesthetic components, which may lead to suboptimal results. To stabilize the optimization process and yield optimal results, we propose a training strategy called soft adapt by importance. To resolve the first challenge, the adaptive weighting strategy rescales the user-specified importance factors, gamma, into appropriate weight factors, according to the numerical scale of each loss component. Basically, if an aesthetic has a larger numerical scale than others, the corresponding weight factor alpha will be smaller. Next, to resolve the second challenge, soft adapt by importance will dynamically adjust the weight factor based upon the rate of descent. In essence, if one aesthetic has not been optimized in the last epoch, then we will put more focus on this aesthetic in the next epoch by dynamically increasing the corresponding weight factor. Here are our quantitative results compared against the SOTA method in terms of stress, which is called NITO. The results of 5 DPGD models with different importance factor settings is shown here. The negative relative percentage indicates that our method is better than NITO by how many percent on average. Let's take a look at the model optimizing stress and angular resolution. Even though these two aesthetics conflict with each other, we can outperform NITO regarding the angular resolution by 22% while still maintaining a reasonably good performance in stress. Also, by optimizing 4 different aesthetics simultaneously, which are stress, angular resolution, node occlusion, and t-SNE, we can actually perform better than NITO from all 4 aesthetic aspects. Next, we would like to show some generated layouts of the same graph compared with NITO. The color of nodes represent their community within the graph, computed by Girvan-Newman algorithm. Unlike NITO, which only focuses on stress, this DPGD model actually focuses on 4 aesthetic aspects. As you can see, for this graph, NITO exhibits some node clustering in this area, while DPGD is able to spread them out more. For this graph, NITO seems to form some sharp incident angle here, while DPGD tends to maximize the angle formed by these 3 incident edges. Here, you can see that this brown node overlaps with some blue node. However, DPGD tries to push them apart from each other. Even though the DPGD is only trained with small graph containing less than 100 nodes, we can still draw a visually pleasing layout for some real-world large graph with thousands of nodes. These results show the generalizability of DPGD on unseen graph even with a significantly larger number of nodes than our training data. For more detail about the evaluation results, please refer to our paper. In conclusion, we propose a novel GN-based framework for graph drawing, which can optimize toward any differentiable aesthetic criteria. Our generated layouts are capable of incorporating multiple aesthetic criteria simultaneously. We propose 2 adaptive training strategies for graph drawing that adjust weight factor dynamically to ensure smooth and even optimization for each aesthetic aspect, considering their respective numerical scale. Both the quantitative and qualitative results manifest the effectiveness and the generalizability of DPGD. Thanks for listening. I'm very glad to take any question you may have.
There's a question from the Slido. Says, as we know that there are many types of graph, such as grid graph, star graph, can this method generate graph with different characteristics?
Yes, even though our model only trained with some general graph, such like this type of graph, however, we can still apply to some graph with special characteristics, such as grid graph, star graph, without retraining the model. So this is because our graph neural network is generalized enough to different topological structure.
For sake of time, let's thank the speaker again, and yeah, nice talk. So now we're going to have the third presentation, interactive visualization of hyperspectral image based on neural networks by Xinyan Xie.
Good afternoon, everyone. My name is Xinyan. So I feel honored to attend this conference and represent my colleagues to present their work, Interactive Visualization of Hyperspectrum Images based on Neural Networks. Hyperspectrum images can provide abundant hyperspectrum information by taking the images of objects at different wavelengths. By stacking all the images along the wavelength direction, they can be modeled as a hyperspectrum cube, from which the users can generate fusion images to identify and explore the substance from the hyperspectrum images. So, hyperspectrum images can be widely used in multiple disciplines, such as plant science, remote sensing, medical image processing, and etc. So when we worked with hyperspectrum images, the users always focus on different aspects. For example, in plant science, some scientists want to study the tassel, but others may be interested in the leaves. And a different part of a hyperspectrum curve can reveal significant different information. For example, when the wavelength is between 400 and 700 nanometers, the curve will indicate the information of visible chlorophyll content information. But when the wavelength is about 1300 nanometers, the curve will show the effect of water on the plant. Moreover, different users pay attention to different substances in the image fusion. Therefore, allowing the users to interactively specify region of interest, select bands of interest, explore and identify substance will be a good option. So here is our contribution. Our works allow users to interactively select regions of interest and band of interest to generate appropriate hyperspectrum information. And we employed a cascade neural network to generate a scatter plot, which can provide the correspondence between the hyperspectral features and the substance. And we also applied the pseudo-colors obtained from the network to each pixel for the substance, which can lead to stable image fusion results. Here is the entire pipeline for our interface. The input will be all hyperspectrum information at all pixel points. By a sequence of interactive modification, the output will be any desired substance in the fused images. I will introduce each part in detail. Firstly, the user can draw a rectangle to roughly specify their region of interest. To get appropriate band of interest, we employed the entropy and intensity mean of the image as our evaluation matrix. Our collaborator showed much interest in the high contrast images, and they can select multiple band ranges. The reduced hyperspectrum information can then be used to generate initial scatter plot by using the principal component analysis. As we all can see, the points here are all crowded together, and their numbered circles at each cluster centers are hard to be distinguished. We allow the users to interactively drag the circles based on their domain knowledge and make it sparsely distributed. And the cluster centers, after brushing, were used as the training target for the neural network. We used a cascade neural network with 3 hidden layers. The input will be derived hyperspectral features at each pixels, and the output will be the 2D position in the inferent scatter plot. The features extracted from the hidden layer will be used as the pseudo-color in the inferent scatter plot and final visualized images. This network can lead to stable visualization results, and it can also provide intuitive correspondence between a feature space and an image space. This is the interface for neural network. The right figure shows the predicted scatter plot. After the prediction of scatter plot with their cluster labels, we allow the users to interactively draw the polygons to select the points, and the corresponding substance will show in the image fusion. Here is an example from remote sensing for Pavia University. Firstly, the user input all the hyperspectrum information into the interface. They specify the entire image as their region of interest and select 3 bands as their band of interest. Initial scatter plot is then generated. The users can then interactively drag the circles to make them sparsely distributed. Targeting at these circles, the neural network can be trained. This is the result for the predicted scatter plot. The users can interactively select the point to visualize the substance in the fused images. For example, this is the middle part and undefined part from the hyperspectrum images. This is the asphalt, brick, and the gravel parts from the hyperspectrum images. And this is a metal sheet from the hyperspectrum images. I'll recap the whole process. Given a set of hyperspectrum images, the users can interactively select the region of interest, band of interest, derive user-defined scatter plot based on the initial scatter plot, and finally obtain the inferent scatter plot and fusion images. From the result, we can see this process can not only successfully segment each substance from the hyperspectrum images, it also releases the relationship between the substance. For example, in the images, the stem and the port are connected, and in the scatter plot, they are also connected. Well, the stem and the frame are not connected in the images, and their scatter plot are also not connected from the scatter plot. Our network can also be used as network transform. It always occurs when a set of hyperspectrum images have similar hyperspectrum range and substance as other hyperspectrum sets. These are sorghum plant over 8 days. They trained on the samples from the first day and used the trained network to infer the scatter plot for the rest of the days without retraining. It can be seen that although the size of sorghum plant changed over the time, but the position and the color at each clusters roughly remain the same. By stacking all the scatter plots along the time direction, a 3D scatter plot can be generated. Our collaborators in plant science have commented that network transform has greatly simplified the process of identifying different substances from the hyperspectrum images in a time-varying situation, and it also provides a more simple and more robust way to explore the individual substance and track their dynamics. Here is our conclusion. Our solutions keep the user in the analytical loop and facilitate them to interactively select substance from the hyperspectrum images. And we also show the significant usage of the trained network transform to other data sets with similar hyperspectrum contents. Finally, our work demonstrated the effectiveness with real-world examples, such as remote sensing and plant science. We appreciate the opportunity from IEEE, the support from NSF, and the help from the Greenhouse Innovation Center at the University of Nebraska-Lincoln. Thank you for your listening.
Thanks for the speaker. I just have a question, like, what's your difference between your segmentation method and regular segmentation method? So it help you identify what that is a stem, that is port, yeah.
So our method is mainly a user-defined interface, and instead of prediction directly on the image, we derive the prediction on the scatter plot, which can lead to a more stable visualization result and provide the intuitive the relation between the feature map and the image map. And our work can also use as the network transform. I think that's the difference between our work and other people's work. Yeah.
Just give the speaker more applause. Thank you. We will have, the next presentation is pre-recorded. It's visual clustering factors in scatter plot by Wei-Xin Lin.
Hello, everyone. My name is Guihua Shan. I am from Computer Network Information Center of Chinese Academy of Sciences. I will use this video to introduce our work, STSRNet, Deep Joint Space-Time Super Resolution for Vector Field Visualization. My presentation consists of the following 4 parts. The computing power of supercomputers far exceeds their I/O and storage capabilities. And we have to face a dilemma. Strong computing power continuously generates massive data, while I/O and storage bottlenecks result in only a limited amount of data transmission and storage. So it becomes impossible to store all the raw data. The massive raw data with high resolution have to be downsampled before writing to disk. The raw data are temporarily downsampled. For example, they are sampled every k steps. Similarly, they'll then be downsampled spatially. Finally, the reduced sample data is stored to disk. The stored low-resolution data have lost many information compared with the original high-resolution data. The stored data need to be reconstructed in super resolution temporally and spatially to recover the lost information before analysis. Our goal is to use deep learning networks to learn a function f that maps the vector fields from low to high resolution. We identified two main challenges of reconstructing time-varying vector fields: the instabilities and complexity of unsteady flow fields, and the reconstruction of spatial features removed from the original simulation output to achieve high visual quality. To address these challenges, we designed a two-stage process. Firstly, we perform temporal superresolution with motion estimation and fusion, and then conduct spatial superresolution. Here is the overall architecture of our method. The input is a pair of vectors in low resolution. After temporal superresolution stage and spatial superresolution stage, we get the prediction K superresolution vectors, and then compute the loss by comparing them with the ground truth. At temporal superresolution stage, the UNet network model is used to estimate the motion state and occlusion, and the input frame is deformed and fused to form each intermediate frame. At this time, it is still low-resolution data in space. At spatial superresolution stage, we extract feature based on deformable convolution. Feature alignment between frames can be carried out without explicit estimation of displacement using deformable convolution network. And features with different granularity are downsampled from top to bottom through the pyramid structure. At last, we get the final high-resolution frames with pixel shuffle. To optimize the whole model, including temporal and spatial superresolution stage, we designed a novel loss function considering the quality of reconstruction, directionality, structures of vector fields, and temporal coherence. We combine them linearly and get the overall loss. We evaluate the models with different combination of loss functions. And as shown in the result table, M3 network achieves the best result according to the evaluation matrix. To demonstrate the effectiveness of our method, we conduct quantitative and qualitative evaluations on 4 different datasets: solar plume dataset, smoke dataset, ESG ocean dataset, and Red Sea dataset. The table provides the detailed information of the 4 datasets. I will demonstrate the comparison of results between our methods and the other 2 methods on the 4 different datasets. Here is the visualization of errors. Compared to the other 2 methods on the left, it's apparent that our method achieves the smallest error. For 3-dimensional data, the visualization reveals how our method also has the smallest error compared to the other 2 methods. As for streamline results for plum and smoke datasets, the ground truth is on the left and our method is on the right. From the diagram, we can see that our method can recover the local small details marked in small boxes, while the two other methods in the middle have lost many detail features. Similarly, as for Pathline, our result is more able to recover the detail features than other two methods in the middle, and is much closer to ground truth on the level of details for the plume dataset and the smoke dataset. Further, we use arrows to depict the flow motion. Our results are almost the same as the ground truth. We also compared the errors of critical points quantitatively. From the result table, we can see clearly that our errors are almost 25 times smaller than the other two methods on plume datasets, and 50 times smaller on the smoke dataset. At the same time, we compared the results using two widely used quantitative indicator, PSNR and MCPD. As the results presented on the table, it is apparent that our method outperforms the other two on both evaluation methods for each dataset. We also compared our method with SZ's compression capacity. Under the same compression rate, our method achieves higher PSNR for each dataset. That is, the effect is better. In conclusion, we proposed a joint space-time super-resolution deep learning-based model for time-varying vector field data. Our method is scalable and effective as it achieves better results on different datasets through quantitative and qualitative evaluations.
Hello everyone, I'm Wei Xinling from
Sorry, I made a mistake. I skipped one of them. Yeah, let's thank the speaker first. Sorry, I skipped one of the questions, presentation. And for your, I think you did a very lot of comparison with other methods. So what do you think? What the sort of why you come out those criteria like complexity, all this, all different sorts of comparison method you used? To distinguish your method from others? Do you have a specific method for come out these criteria to compare for comparison?
Yes, one important is our loss function is quite different. It's employed the compress for each of the first is magnitude and the cosine distance and the geography loss and the temporal loss, which makes the use of the physical feature of the date, which can describe or capture the physical feature of the date. I think that is very important. And we also joined the temporal super reconstruction and the spatial super reconstruction together. Thank you.
Let's give some more applause to Guihua Xuan. Thank you. A really nice one. Next, for the next presentation, it's also a pre-recorded presentation, visual clustering factors in scatter plots, presented by Wei-Xin Li.
Hello everyone, I'm Wei-Xin Li from Central South University. In this work, we explore visual clustering factors in scatter plots. How do people visually recognize clusters in scatter plots? What are the influence factors of visual clustering in scatter plots? Is it possible to build an automatic clustering model to work as human perception? We conduct a data-driven study for these questions. To obtain cognitive information on human visual clustering by the data-driven method, we construct a labeled scatter plot dataset. We simplify the problem as containing only 2 clusters and identify a set of visual clustering factors with literature review and expert review. Let me introduce these factors. The shape factor refers to contour formed by the cluster boundary. There are 3 shape types: polygon-based, plane-based, and curve-based. The texture factor refers to distribution type of data points. It has 3 types: uniform random, equidistant, and one-dot spot. When 2 clusters obey different distributions, there's a difference in texture. The area factor refers to the area covered by a single cluster. The variance of area is defined as the area ratio between the 2 clusters, which is set to 5 levels from 1:1 to 5:1. The position factor refers to the spatial relationship between 2 clusters, which has 6 types: separate, touch, neighbor, overlap, intersect, and include. The distance factor refers to the distance between the boundaries of 2 clusters. It is only defined when the position is overlap and separate. The distance is set to 3 levels: 10 pixels, 20 pixels, and 30 pixels. The density factor refers to a number of data points in a unit area. The variance of density between 2 clusters refers to a difference in their density, which is set to 6 levels from 0 to 1.5. The angle factor refers to the angle between the contours of 2 adjacent clusters. It is only defined when the position is neighbor. It is set to 6 levels from 30 degrees to 180 degrees. The noise factor refers to adding random noise to the dataset. The noise density is set to 6 levels from 0 to 0.5. Then, we generate a control dataset for each candidate factor by sampling in the factor space. Each control dataset is formed by groups, which have distinct values of a target factor and share the same values in all other factors. The control datasets of factor contain 40,864 scatter plots. In addition, we really sample 10,000 scatter plots to cover more cases. We also collect 51 real datasets and made 1945 scatter plots. Then we organize 3 experts to label the datasets. There are 2 labeling tasks: the classification task and the identification task. In the classification task, the experts indicate whether there are 2 clusters. The 3 labels are merged into one by majority voting. In the identification task, the experts identify the 2 clusters. Among the 3 labels, the label that has the highest similarity to the other 2 is regarded as the final label. Next, we analyze the label datasets to identify the influence factors of visual clustering. Before factor analysis, we count the 4 types of labeling results and make charts. We can analyze the impact of factor by observing proportion changes in labeling results under different factor values. The figure shows the labeling results of the factor position, shape, noise, and angle. Position, noise, angle are influence factors because their proportion of labeling results change a lot under different factor values, while shape is not an influence factor, especially position is a decisive factor. In separate, 97.5% of scatter plots are labeled as 3 positives. This shows that other factors are ignored. Then we analyze factor distance. First, the figure shows that distance is an influence factor. Second, we found that as the distance increases, the clusters are easier to identify in separate, while in overlap, it is more difficult to identify the clusters. Next, we analyze factor texture. First, texture is an influence factor. Two clusters with the same texture are much harder to visually identify than those with different textures. Second, position affects the effectiveness of texture. For example, EQ labeling results in neighbor and overlap are much different. Third, we found that the impact of ODS distribution is different from that of EQ and UR. In neighbor, ODS is easier to identify than EQ and UR, while in intercept, ODS is more difficult to identify than EQ and UR. We found that error is not an influence factor because as the variance of error increases, the trend of the curve is not obvious. The next factor is density. First, we found that density is an influence factor. The figure shows that as the density changes, the results are quite different. Second, the effect of the density factor is different under different position types. The intersection point of the red and blue curves are different in neighbor and overlap, which indicates that in overlap, higher density is required to enable the experts to identify the two clusters. Through the factor analysis, we find out the influence factors. Factors shape and area are not influence factors. Factors texture, distance, position, density, angle, and noise are influence factors. Among the influence factors, the position factor is the decisive factor. The influence factors of visual clustering are clear, and is it possible to model human visual clustering? Convolutional neural networks can capture multi-level visual features. Therefore, we assume that convolutional neural networks can model human visual clustering. We conduct a classification model and an identification model. Both of the model's inputs are scatter plot images. The output of the classification model is positive or negative, indicating whether there are two clusters in the image. The identification model identifies the clusters in the images and outputs the pixel level result, which will be converted into point level results. We test the classification model on a subset of each candidate factor. The model achieves high performance on all factors, which indicates the model successfully models the visual clustering in scatter plots. We also compare the identification model with commonly used clustering algorithms. The model has better performance than the traditional clustering algorithms on all factors. To sum up, we constructed a labeled scatter plot dataset, identified influence factors of visual clustering, and modeled human visual clustering perception. Through the study, we have a better understanding of human visual clustering. That's all of my talk today. Thank you.
We have a question from Lin Chen Huang from the Slido. Why do you simplify like the problem as containing using only 2 clusters instead of using 3 or more?
Oh, it's a good question. Can you hear me?
Yes, yeah, we can hear you.
Because containing 3 or more clusters will greatly increase the amount of data and increase the cost of labeling. We think the cases of 2 clusters will be complex enough for this preliminary study on the visual clustering perception problem.
Just extra follow-up. Do you think like there was some different, more complex using or other artifacts using like 3 clusters or 4 clusters?
I think using 3 or 4 clusters will be more. The mechanism will be more complicated than that in two clusters. But we only can simplify the problem because we have not enough people to label the data.
There's another question from Xin Zhao asking, is the mechanism inside the classification model consistent with human visual clustering?
It is a good question. Actually, we do not verify whether the mechanism inside the model is consistent with human visual clustering. Maybe we can verify it using methods in expandable machine learning, such as saliency map.
Let's thank
you.
Yeah, thank you. Let's thank the speakers again.
Thank you.
Now we're going to have our last in-person presentation by Sean Daniel Faketa on Carlo Lab, a web-based scalability visualization of large document collections.
Sorry for that. Setting my resolution right. Okay, good. All right. Here you go. All right, thanks. Hi, everybody. Sorry, I'm the last one before the restaurant tonight or anything. So I'll be talking about this project, which is for me very important. It's called Cartolab, and this project is about the visualization of large document collection on the web using multidimensional projection. So this project is done with all my colleagues from Université Paris-Saclay and CNRS. So what is Cartolab? Cartolab can be defined in 3 ways. Initially, it was meant for visualizing the all of the publication done in France, because in France, when we publish, we have to put our publication in a public repository. But then it became usable for any kind of document repository with millions of documents if possible. So if you go to see cartolab.fr, like here, you will be able to access archive or HAL or Wikipedia or other with millions of documents using multidimensional projections. But then actually, Cartolab became a system, a toolkit for allowing you to apply visualization to large document corpora, either because you have large document corpora and you want to visualize them and that's it, you take it, you use it, or because you are a visualization researcher and you want to be able to better visualize document corpora, but you don't want to care about NLP or all of the things around it. So you take it, you use it, and you develop your own visualization or you improve it. Or you are an NLP researcher and you want to develop new NLP methods, but you're not a visualization researcher, so you don't want to do the visualization part. So you take it, you use the visualization part, and you improve the NLP. So I'm going to explain to you how it works, and it's a bit special because you will find several systems that say, I am using multidimensional projection and document to visualize them. Good. But they do 90% or 80% of the work. But in order to make it really usable and really useful, there are a lot of small things you need to do right. And that's what we have tried to do with Cartolab, to do everything required to do it right. So I'll go into a few details. So here is an example of Cartolab. That's what you will get when you get to the website. So this is basically showing you two colors here, blue and red. So that's the publication of all the French publications, scientific publications. The blue things are documents, so papers. The red things are authors, okay? All of them are projected in the same space. So basically, the authors similar will be close by, the documents similar will be close by, and the document made by authors will be close to the authors, etc., etc. So there are two, the same are in the space. What you can see also in this visualization is that you see labels. You see the yellow labels. The yellow labels are area labels. They tell you that this area is about computer science and this part of, or astronomy or something else. We generate them automatically. You give them a huge document collection. It generates the map, plus it generates the labels on the area, and that's a hierarchical thing that generated. And you see some documents names highlighted and some team names highlighted or person's name highlighted. Why those? Because we also have a mechanism for showing the most important person items so that you have labels, so you know what is there, but you don't label everything or things at random. Okay? Then you can zoom in, you can search. So here I search on my name, then I zoomed on my name, and then you can see around me all the main person and all the main group, etc., visualized at scale. So this one has about 1 million document and about 4 million people visual. And you can see who are my neighbors, etc. So, and you can do the same. It's done with archived data sets. So you have in archive many kind of topics, and it retrieves them, and you can navigate on these topics and see their shape. So, and that's Wikipedia. So in Wikipedia, you don't have authors, or at least they are not visible, but you have Wikipedia with 5 million documents, okay? So Cartolab is a research project, actually. We wanted to visualize all these documents, but we also wanted to make it easy for researchers to do their research and have something working, okay? So it's an open source tool. And we provide all of the pipelines for treating all the things in the open source tool. So you can start from an existing pipeline, HAL or archive or others. There are many of them, and tweak them for your own use. And the most important, I will be talking about that today, are all the small things that not so small actually, in order for these techniques of projection and navigation to be really usable by users. So I will talk about that. So just a simple explanation. When you go to the Cartolab repository, it will split in two. One is the NLP pipeline, and the other one is the visualization pipeline. That's kind of easy. So the NLP pipeline looks like that in general. You can change it easily, but that's how it works for all the French publications. So in the beginning, it's pretty simple. You have all the documents that are coming on the top left. And then you extract what you want to do in order to do the projection. You apply some topic modeling or some more modern Word2Vec or machine learning method in order to do the projection. So here we use LSA with 300 dimensions, let's say. This gives you a first set of vectors. On that vectors, you add a scoring of the importance of every item. So for every user or for every document, you have a scoring. In our case, the scoring can be done either by knowing how many authors there are or how important the people are. We can also look at the stats of the use of our HAL database. That's what we do. So you have a scoring that gives you what are the important articles and the less important ones. So then we compute the UMAP projection. That is pretty standard, except there are some caveats, but I'll talk about it later maybe. And then on top of that, in order to compute the area labels, we apply a clustering. And so again here, what we do for this simple case is we apply k-means clustering, which is good enough. The k-means clustering will find a series of about 8 areas and then does recursively more 8, 8, 8. And in these areas that has been found by the clustering, it will collect the main words and find the most important words for them to do the labeling of those areas, okay? So again, if you go on the web, you will find maybe 50 different projections of documents, but they never provide area labeling. They just start and they are talking about it, but none of the disclosed things are doing it. And then we export it, and you will find all of our exported projections available in the Zenodo repository, so you can use them even without Cartolab. We give everything in open source, so you can reuse our projections. Then from that, we go in the visualization pipeline, and the visualization pipelines uses the projection data and create pyramids of tiles. Okay, that may seem standard to you. But again, when people do projections, most of the time they keep the point and they send them to the browser. So if you start a projection on your browser, it will take from 5 seconds to 2 minutes to download everything. And of course, since we are all visualization people, we'll all expect that we'll have a huge GPU with a lot of memory, and that's not the case for most people. So in our case, we don't rely on sending anything to the GPU. We just create tiles that we will solve later. But what we do is we create a set of tiles for every type of object that we represent. We have tiles for the authors, tiles for the documents, and we compose them at the front-end level, so we can decide which one we want to see. And so we can see them separately. So we have a paper on how to do this kind of compositing and more. So the point that we are trying to do is to say, okay, you are a software, you are a developer, you want to try a new visualization. Well, do it with Cartolab, take it, use it, and then modify it to be more efficient for what you need, what you want to do for your own feature. And if you are an NLP researcher, do the same. If you can try all of the algorithms you want, all the new projection methods or the new models, language models, in order to train the projection and test whether it's better or it's not better. But additionally, we have all of these features for helping people to navigate, search, and label everything, etc. in the visualization. So that's it. And do I have a bit of time? I can do a demo then on the system because it's kind of right. So yes, if you go to Cartolab, then that's what you get. That's the French repository. So again, I'm on the Wi-Fi, and the site is in France. So I can type my name. and then see who are the persons who are closest to me. So here I am. You can see where I am overall. So they put me around human agents or computing power, machine artificial intelligence, etc. I can see who are my closest neighbor, and they are listed here. And so I can see also what are the close-by organizations that I have around me, or the close-by papers that are around me everywhere. Sorry. So some papers that have the closest thing. So this is scaling to millions of points, and you don't need any particular machine to use it. You can probably do it on your own machine. And you can also use it for scaling to 10 millions of documents using a few pipelines that we provide. So if you have questions, ask me, and it's been really designed for helping researchers, so don't hesitate to contact me. Thanks.
There's a question on Slido, says, can we use a different data set in Cartol? If so, what format would be?
Different what, sorry?
Data set.
Oh, you can use any data set. So we provide pipeline for about 10 to 30 different data sets that are downloaded from the web. So archive is downloaded one way, HAL is downloaded another way, Wikipedia is the third way. So the pipelines show you how to download the data from any kind of source, any size, and yes, you can. And the format are described, it's very flexible. So you can see the examples. We have Python notebooks to show you how all the steps are done, and you can play with them interactively and see the result before you apply that in a batch format. So yes, you can use any kind of input format. It's very flexible.
Yes, thank you for the nice demo. Let's just give the presenter one applause. Thank you. Thanks for the speakers and the audience in the room to join this session. Enjoy the rest of your day and have parties. Yeah, thank you.